started. All right, thank you all for joining me on a non-traditional day for the DTM seminar. I'm really happy to present Helen Janiszewski. She's coming to us from Lamont. Helen got her bachelor's degree at Rutgers University, working with the Dean Levin there in geophysics, geological sciences and physics with minors in math and Russian language. That was in 2012, and then she moved just a titch further north to join Lamont with a graduate research fellowship from NSF. And she started working with Jeff Abers there until Jeff moved further north as well. And so she continued to work with him, but then also working with Jim Garrity. And I don't know, are you working with Donna as well to some extent?
Not currently. I work with her.
There you go. So Helen did a lot of work on subduction zones, in particular using offshore and onshore data, which is a difficult and neat trick. And she'll be talking to us today about Cascadia. So, get that turned on.
Okay. Well, thank you all for being here today. So the title of my talk is Shoreline-crossing Shear-velocity Structure of the Juan de Fuca Plate and Cascadia Subduction Zone from surface waves and receiver functions. And I'd like to acknowledge my collaborators on this work, Jim Garrity and Jeff, who are my advisors, Haiying Gao, who provided the ambient noise data, Zach Alon, who helped with the formulation and testing of some of the noise correction codes, and Spar Webb, just for his immeasurable wisdom with dealing with offshore instruments. Before I start, I'd also like to mention that most of the data I'm going to be showing you today is from the Cascadia Initiative experiment, which was a large 4-year community experiment that covered the entire Juan de Fuca plate with ocean bottom seismometers. And I just would like to acknowledge all the people that put effort into making this experiment happen, the people that went out onto ships to deploy and recover these instruments, and the 3 instrument centers, Scripps, Lamont, and Hui, that design and maintain the instruments. So to start off, why do we want a shoreline-crossing shear-velocity model? And so I'm going to highlight a few questions that having such a model could help us to answer. And I'm just going to go through these very briefly, and then we'll talk a little bit more about the basis for these questions afterwards. But so the first question is, what can we learn about the evolution of a plate from its creation at a ridge through the entire subduction process? Another question is, how is heterogeneity of thermal and compositional properties linked to variations in subduction behavior? For example, episodic tremor and slip at subduction zones, or segmentation of the megathrust. What does the transition from locking to stable sliding along a subduction plate interface look like? And the fourth question, which is less motivation, but something that we can learn from analyzing this type of data, and that is very helpful for also answering these questions, is how can we most effectively use ocean bottom or seismometer or OBS data in different frequency bands, and what sort of techniques and things do we need to be careful of when dealing with this type of data? So to revisit the first question, here we have the Cascadia subduction zone, the Juan de Fuca ridge, where the Juan de Fuca plate is created, then moves eastwards where it hits the North American plate, and then begins subduction at this thick black line. These thin lines are just depth, 10-kilometer contours to depth of the top of the subducting plate. And so what happens to this plate from when it's created here to when it begins subducting? Does it get created and then just kind of stay the same the whole way, or do various alteration processes happen to it to alter what the plate composition might be as it progresses eastwards? And if we look at kind of some detailed structure of what this plate looks like, so these colors are just isochrons from magnetic data moving from the Juan de Fuca ridge here, and we can see these discontinuities, which are called propagator wakes, and these are areas where the ridge has potentially migrated back in time. And so these areas are regions that are highly fractured within the crust, and therefore you might expect there to be variations in how much water is locally present. You know, some questions are, how altered does the crust become? How deep would this alteration travel down into the mantle? Is this a process that is maintained over long time periods? And you know, what sort of heterogeneity do we expect along the plate if these processes are very localized to small regions? Moving on to the second question, how is heterogeneity of some of these properties linked to subduction behavior, just to show as one example for looking at megathrust segmentation. Cascadia, we know, has had large, probably up to magnitude 9 earthquakes in the past along its megathrust, the most recent of which happened in 1700. And so there's some studies that suggest that the rupture along this interface is not just simply a homogeneous rupture. For example, here, this is gravity data showing in these white circled regions are gravity lows that represent sedimentary basins, and they are thought to be indicators of where subduction erosion has happened in large megathrust events. So the plate would have, the plate interface would have ruptured more greatly in these circled regions than in the surrounding regions. So this points to there being some heterogeneity in the behavior of the plate interface. And similarly, if you look at episodic and tremor and slip, these colors just indicate the recurrence time for different regions of episodic tremor, and you can see a long strike variation in how often these processes recur. And so what is driving that? Is this the incoming plate? Is variation in the incoming plate driving some of this variation? Is it the overriding North American plate? Is it the interaction between them? What sort of structures are there structures that are linked up with this variation that we see in behavior? As I just mentioned, we're talking about megathrust, earthquakes, and episodic tremor and slip. That represents the transition from where the plate is locked, plate interface is locked, to where it is stably sliding. And so what does this transition look like? The figures shown here are just two models that match onshore geodetic data of what the locking along the plate interface is. So the red colors would represent where the plate is more locked, blue colors represent where it's freely slipping. And you can see that there's quite a lot of variation along strike of the plate interface and how much it may be locked. And also you'll notice that the majority of this is offshore. So to really understand what sort of structures may be present where the plate is locked and what this transition from where it is heavily locked to where it is stably sliding looks like, you need both offshore and onshore data. And so this is just an example of a seismic result from using onshore data in Cascadia. This is from the Café line, which is shown approximately extending here. This is just variations in shear wave velocity model in cross section, so the depth is the y-axis. And what of the results from this, and then also other studies along the coastline here, is that you can see the subducting oceanic moho, but you also get a strong velocity crust at the top of the plate, which represents a low velocity zone. Potentially either metamorphosed sediments that are going down with the crust or elevated pore fluid pressures. But to extend a picture like this offshore and also into the transition where you get into the lock zone, you need offshore instruments to seismically image this region. So the approach that we're taking to answer some of these questions is we're going to start out using seismic data, part of the Cascadia initiative, and simultaneous experiments to calculate receiver functions and Rayleigh wave phase velocities, and I'll give you a brief background of what those techniques are. This is the Cascadia initiative data. All of these little white symbols are stations that we are using, so it covers the entire Juan de Fuca plate all the way out here from the ridge to behind the volcanic arc. Then we can leverage complementary constraints on the seismic shear velocity from these two different data sets in a Bayesian joint inversion. This allows us to simultaneously determine shear wave velocity structure at both the crustal and plate interface scales as well as mantle scales. And then, of course, the final step is we want to relate the seismic velocities that we solve for to physical parameters such as temperature, composition, hydration. Now, in this talk, this is a work in progress, so I don't have interpretations directly of what the temperature structure might be in this region so far, but what I'm going to show you today are results from our receiver functions and Rayleigh wave phase velocities and the beginning of some of our shear wave velocity models using these techniques. Then I'm also going to address this fourth question that I had up in the beginning, and that is some of the techniques that we've used to really effectively use the OBS data in the receiver function and surface wave bands. The receiver functions are at higher frequencies and the surface wave bands are at somewhat lower frequencies. So what you have to do to the data varies a bit. Okay, so now to move on just to a brief overview of the methods. So receiver functions and surface waves. A cartoon illustrating what receiver functions are is shown here on the left, and surface waves is shown on the right. Receiver functions, where we have a seismometer recording teleseismic earthquakes, the rays that pass through the interior of the Earth are used in receiver function studies. And what receiver functions are most sensitive to are abrupt velocity boundaries. And so just shown here is a cartoon where you have a P wave that comes up and is recorded at the seismometer, and then if you have an abrupt velocity boundary, it will also convert to an S wave, and you'll get these multiples as well. The important thing to take away from this is that by using these recorded phases, we can get some estimate of what the shear wave velocity is of this layer and what the depth of this boundary is. For surface waves, instead we're using rays that pass along the surface of the Earth, and they have an important property called dispersion. So this means that different periods will travel at different velocities. This is because short periods are sensitive only to the very top part of the surface of the Earth, whereas as you extend to longer periods, they become sensitive to deeper and deeper portions of the Earth. Since seismic velocity with depth is not constant, this means that the velocities will change as you move to longer periods, and typically velocities get faster as you go deeper. So this is why here at 60 seconds period, you see the seismic waves arriving before waves at 20 seconds period. This is just a number telling you what narrowband filter these seismograms have been filtered at. And so we can put the information from the velocities at these different periods together to learn about what the velocity structure with depth is beneath these seismic stations. But importantly, in contrast to receiver functions, this gives you a continuous estimate of velocity, so it's not sensitive to abrupt boundaries. Though features like that will get kind of averaged out in surface wave studies. So if we put the two of these results together, not only does the surface wave velocity estimates give us a better starting model for our receiver functions, but the receiver functions in turn see more detailed abrupt velocity boundary structure that the surface waves are blind to. So putting these two techniques together is very useful for getting a more detailed picture of the shear wave velocity structure. So now I'm going to walk you through some of our results that we have from just the receiver function part of the study. So this work is already published. This is just looking at the northern half of the stations. They are color-coded by how many earthquakes we were able to use at each station for calculating receiver functions. So we use receiver functions from multiple different earthquakes, and then we can stack them to eliminate some noise and get an estimate of what the structure is beneath the station. So essentially, the darker colors mean it was a station with higher signal-to-noise ratio. And you can see that for the majority of the stations, while there are some that work out on the ridge, a lot of the ones that work quite well are in shallow water over where the plate has already begun to subduct. And so all that I'm going to show in this talk today is just focusing on receiver functions from these stations within this box called the Grays Harbor Focus Array. But before I show you the results from the receiver functions, I'm going to just take a step and talk briefly on the side about the effects of water noise on receiver functions and what we do to avoid these problems. So what I'm showing here is coherence between our pressure and vertical component. So all OBS stations are deployed with a pressure gauge that measures how much water is on top of your OBS instrument. And this is just showing it for two different stations, one that was deployed at a water depth of about 1,500 meters, and then another one in this solid black color, which was deployed at a shallow depth of 158 meters. And you can already see just very obviously that the signature of coherence between pressure and vertical looks very different between these two stations. And so this high peak at long periods is caused by something called the infragravity wave. And that basically just means that as a water wave is traveling over your little OBS, the seafloor actually moves up and down due to the loading of this wave. And so you get a signature where your pressure and vertical component are basically in sync with one another. And that's problematic if you want to measure something where instead you're dominated by a wave-generated noise. But what's interesting for receiver functions is that we can just basically high-pass filter out all of this noise, and we use this frequency band when, if you look at, for the shallow water instrument, it's at a low between the coherence between the pressure and vertical. So we don't need to do any fancy corrections for the receiver functions at instruments in shallow water. We can just filter it to get rid of all the problems, which is really convenient. Another issue with receiver functions in water that has been problematic for people is the fact that you get water multiples. So if you have seismic waves that are being recorded at your instrument, the P wave can then actually bounce up and down in the water column and interfere with the arrivals that you're looking for from boundaries below. And what I'm just showing you here is a predicted receiver function for different water depths on top of a MOHO interface. And the main thing to take away from here is that if you look, the water at 0 kilometers versus 250 meters, the receiver function is basically identical. So at the frequencies that we're looking at, which has a low-pass filter of 0.4 hertz, we can filter out water multiples up to a depth of 250 meters. So the takeaway from this is that basically clever filtering and use of shallow water OBSs removes the water noise problems that typically plague offshore receiver functions. So hopefully this will convince you that we've gotten around these problems for dealing with receiver functions in this environment. So now we're just going to focus in on the results from these stations. And so what I'm showing you here, each one of these columns is a different instrument. These are individual receiver functions recorded from, calculated from different earthquakes at each one of these instruments. The water depth is given next to the instrument name. This is the y-axis in time, where 0 is where the P wave arrives, and then these are just seconds after the arrival of the P wave. And so we classify these into kind of 3 different segments. You have a deep water station, shallow water stations that are in these trawl-resistant mounts, which are these big steel kind of covers for the OBSs, and then one onshore station, which you can see has significantly more earthquakes than the offshore stations because the data quality is much higher. And this is just a cartoon to remind you what receiver function looks like. Here are the rays that we're talking about, and the P wave and these multiples come in positively, where they're indicated by a black pulse, and then a negative arrival is indicated by a gray pulse. So a few things to point out here is not only do we see quite a lot of consistency between arrivals from different receiver functions at an individual station, but we also see quite a lot of consistency across this densely spaced array, which is really useful for us to diagnose whether or not these receiver functions are imaging structure, because the fact that we're seeing the same sort of arrivals gives us confidence that this is actually imaging structure beneath the station. And so the main phase that you see here is this P to S conversion off of the subducting MOHO. And then we have a negative phase that you can see at many of these stations here that comes in quite nicely, which is this negative PSS phase from the MOHO. And then we see a few other consistent phases, although largely in here there's less coherence than with these main phases, and I will explain why that is in just a moment. But this is really exciting that we actually are able to use this technique for imaging in this region, because receiver functions offshore have been really, really challenging in the past. So this is a really nice result that we actually see these clean phases coming in. And so what we did in this study is we wanted to try and see what sort of velocity structure might explain this receiver function these receiver function phases. So shown here is a forward modeling example that we looked at. This is just the stack of the receiver function for this particular instrument, FN07. The black lines indicate the data, whereas the dashed line are synthetics generated for the velocity model that is shown down here. This is the same instrument, it's just at two different filter periods. And we tried a few different modeling scenarios, which I can show in more detail if people are interested, but the takeaway from this was that we found we needed a low velocity zone at plate interface depths in order to explain the fact that we have these really strong these really two strong arrivals, but then we don't have much of an arrival in between them. And so this is the model that we generated. Here is the subducting moho, here is the oceanic crust, and then at somewhere around plate interface depths we have this low velocity zone. So just again, takeaway, the receiver functions were successfully calculated at these shallow water OBSs, and we have some sort of a low velocity layer at the subducting plate interface, and this is within where we would predict the plate interface to be locked. So we're going to come back to that later, but now I'm going to transition over to the surface wave side of the analysis of the data. So just very briefly introducing you to the two types of data we're using. So we have ambient noise data. This means from across an array of seismometers, we are able to just record the ambient seismic noise field. And we can use then cross correlations between the different instruments to measure the velocity at which this noise is propagating. So this is just an example of cross correlations of noise for a single OBS station. So you can see this is the station distance, and as you get farther away from the stations, the correlation moves out in time. And then for those of you that are familiar with this technique, we're just using a Bessel function fitting method to calculate the phase velocity curve associated with the ambient noise. And I should mention, so the ambient noise gives us estimates of what the seismic velocities are at short periods. Then to get to longer periods, we use data from teleseismic earthquakes. And just briefly to go over the technique that we're using, first we measure differential travel times of a particular phase at a particular period across the entire array. And that basically gives you a travel time gradient, which you can then translate into a phase velocity measurement. Then from that you determine the direction anomaly from the great circle path of wave propagation from the earthquake to the station, and then you measure the variation of amplitude at stations across the array. That amplitude information tells you about whether or not the rays have been focused or defocused by high and low velocity anomalies. And then we use something called the Helmholtz equation, which basically uses the amplitudes to take account for these focusing effects. But again, before I move on to showing you the results from the surface waves, I want to take a step back and talk about the effects of water noise on this technique. And if you remember, for the receiver functions, this was the band that we were working in. But now for surface waves, we're going from about 10 to 100 or so seconds. So we've moved down to this band. And this is right in the middle of where we have a very strong infragravity wave, so we need to remove this noise. This is just showing coherence for two stations. So again, this is a measure of how similar these different components are. The bottom is pressure to vertical again. The middle is the vertical with the first horizontal component on the seismic station, and the top is, or the second horizontal component, the top is the first. And again, this is just comparing two stations at different water depths, shallow water and deeper water. And the main takeaway from this is just simply that noise at these stations does not look the same. The noise that you get is actually very dependent on what type of station you're using, what water depth it's in. So for example, here we have something that's called compliance-dominated noise, and that is the waves moving over the station. Whereas at this station we have something called tilt-dominated noise, and you see that there's pretty high coherence between your vertical and horizontal components, which means that the instrument has been deployed and actually is tilted a little bit on its side, so you have leakage between these two components. Now, fortunately, we can actually correct for all these problems using already pioneered techniques by Webb and Crawford and others. And so this is just an example of what the original earthquake looks like for these two stations before we do these corrections, and what it looks like afterwards. And you can see it's a huge improvement for what the data looks like. But most importantly, what we found is that it doesn't just improve your data quality to do these corrections. If you don't do these corrections, you actually get the wrong answer, which is really scary because these techniques are not always used equally by people in the OBS community. And so this is just a comparison of 80 seconds phase velocity map using the data where it hasn't been corrected for tilt and compliance, and using the data where it has. And so you can see on shore, the results are pretty much identical, but as you approach the coastline, and particularly as you get offshore, the velocities that you get, which are indicated by color here, are hugely different. And so if you're going to go and interpret these velocities in terms of temperature variation, compositional variation, if you use data that hasn't been corrected, you will get a very wrong answer. So this is basically just a plug to say that these corrections can be a really essential part of the OBS surface wave, and it's not just the fact that you're improving your data quality, it's that you can actually go very awry without doing these types of corrections. But to move on now to the results. So these are phase velocity maps from the ambient noise and teleseismic earthquakes. So the colors indicate phase velocity, so warmer colors indicate slower phase velocities, blue colors indicate fast velocities. Each one of these is at a different period, going from 15 to 80 seconds. And so 15 seconds are going to be predominantly sensitive to crustal, maybe some upper mantle structure, whereas 80 seconds we're moving down to more deeper mantle structure. Well, we're moving deeper to lithospheric, maybe some asthenospheric structure. And and one thing to point out also here is that at 20 seconds we have overlap between our result from the ambient noise and the result from the teleseismic earthquake, and we compare these two phase velocity maps and see that in general they look pretty similar, which tells us something that, okay, both of these techniques are giving us probably the right answer. But we can start to kind of look at some of the features that we see in these phase velocity maps and interpret them in terms of structure. Now, this isn't a quantitative relation between seismic velocity and temperature or composition, but we can start to learn something just from looking at this. And so very clearly, we can see the transition between oceanic and continental lithosphere. So here we have at the shortest periods, we're already sensitive to oceanic mantle structures, so the velocities are quite faster offshore, whereas then when you transition to the continental crust, we're primarily sensitive to only the crust, and so the velocities are quite slower. We can also see signatures of the ridge and plate cooling. So in general, with seismic velocities, slower velocities can indicate warmer temperatures, whereas faster velocities can indicate cooler. It's of course more complicated than that, but you can think about it that way when looking at these results. And so we have these slower velocities here at the Juan de Fuca and Gorda ridges, and then as you move away from the ridge, we very clearly see it getting faster as the plate begins to cool farther away from the ridge. And we see this pretty thoroughly at all of the periods that we're looking at, although some of the ridge signature starts to disappear a little bit at the longest periods. Another thing that we see is the front of the subducting slab, which if you look at 50 and 80 seconds period, all of a sudden you see this faster kind of velocity anomaly creeping under the North American plate, and that's probably, we're seeing the Juan de Fuca going down in a map view. And we also see evidence for the Cascade volcanic arc. Slower velocities here, following the arc somewhat linearly. Again, we see this pretty much at all periods. Interestingly, there looks to be north-south variation with how slow these velocities are, particularly at longer periods. For example, at 50 seconds, you can see a slow patch that is really centered around this northern group of volcanoes, and then a broader slow patch centered around the southern group of volcanoes. So there might be some interesting features there that could be related to some variation in structure around the volcanoes in the arc. And again, just to point out some hints of a long strike heterogeneity that we're starting to see if we bring up these pictures again, where we're looking at these sedimentary basins and the long strike variation in episodic tremor and slip. These circles are kind of very roughly drawn approximately where some of these gravity lows are. And we can see as we move from 15 seconds down to longer periods that maybe there are some slow velocities associated with these. And I mean, that's obvious. If there's a sedimentary basin, it should be a very big package of slow velocities, so we would expect to see that. But if you look at this, it actually, at 20 seconds, we still see maybe something at a few places. And again, here at 32 seconds. And as we move down to deeper, longer periods, the signature kind of starts to get lost. Although there is, interestingly, still this kind of slower velocity feature up here all the way at 80 seconds. So it's an open question whether or not this is all just surface structure that's kind of bleeding down to these deeper levels, or is there some deeper variation that these phase velocity maps are seeing that they're sensitive to? But in general, the takeaway is that we have phase velocity maps from 15 to 100 seconds, and they are successful in imaging tectonic structures from the ridge through subduction. So this gives us a really nice, robust data set to start with when we're doing our inversion. So now I'm going to talk briefly about the Bayesian joint inversion process. And so, like I said, this is a work in progress. And so for today, I'm just going to show you an example from this one station, which is just offshore Grace Harbor. This is the region that we were looking at for the receiver functions in the beginning. And this is, again, a station that should be within the lock zone of the plate interface, and it's offshore. So this is a shear wave velocity model. So here, the x-axis is Vs, and then this is depth. And so we're moving down from the surface to the mantle structure. The warmer colors indicate regions where the model is higher probability. So you can kind of roughly follow this dashed line through the center, and that is the mean of all of our models. This technique, basically, you put the receiver function and surface wave data in, and it does 500,000 iterations and comes out with a probabilistic math of what your model should look like. Shown here on the right are receiver functions and our phase velocity data. The red is our receiver function data. The black lines is just a sample of the synthetic receiver functions generated for the suite of accepted models used in this technique. And similarly for the phase velocities, the red dots indicate our data, and the black lines indicate the synthetic results from this model. And so what we see here is we can start out at the surface. These slow velocities are probably a package of sediments on top of the continental shelf. And then we move down, and all of a sudden we start hitting these low velocities. And now this is about 1 kilometer-ish thick. Then it increases in velocity. This whole package here is about 5 to 6 kilometers thick. So that is probably our subducting Juan de Fuca oceanic crust. And then we move down into higher velocities in the mantle, which is right here is our subducting oceanic moho for the Juan de Fuca crust. Right now we're just only going down to 80 kilometers depth. We can probably expand on that a little bit, but we haven't done that quite yet. And so you can see too that the data is being fit reasonably well, although there are some differences. For example, this difference where the synthetic data is over-predicting the amplitude of our initial P-wave arrival, that probably has something to do with the fact that the sediments are not being mapped as slowly as they should be. The slower you have your shallow sedimentary structure, the more reduced this amplitude will be. But there's a trade-off between how complex it wants to make the model. So it might be that it's just preventing it from getting quite as slow as it needs to be. But if you'll notice, one of the major features where this data fits the best is right here in the middle, around between 5 and 10 seconds. And this is very important because this actual lack of features is kind of the most robust evidence for the fact that there's some low velocity zone here, because you get interference from phases that come from this feature and then your subducting moho. So that seems to be fitting quite well. But again, this is an entirely data-driven result, and it really wants to have some sort of a low velocity zone at the plate interface. And so, yeah, as we say, they're successful in imaging detailed structure of the subducting Juan de Fuca crust, and we also have sensitivity to the underlying mantle. And then moving on back to looking at what we started with, where we have these seismic results that have looked at what the structure of the subducting crust is offshore, and now we want to understand what is happening with the subducting plate offshore. We have evidence that there is some sort of a low velocity zone, potentially within the lock zone. And what that is unclear. Maybe it has to do with some sort of a shear zone, a weak shear zone. You know, maybe it's something where slip has happened in the past, and there could be maybe anisotropy associated with that that's slowing things down. Or maybe it's just very fractured. This is going to be something that we further investigate, and it's also going to be very interesting to find out as we move to completing this inversion across the entire margin, whether or not this is a feature that is seen everywhere, or if it's a feature that's localized to certain regions. And if it is variable, how localized is it? Can we see it at the resolution that we're using, or does it get kind of smeared out? And that will hopefully inform what sort of scales we want to look at for structures like these if we're planning future experiments to get at more information about what the plate interface structure looks like. But in general, where we have it right now, so we have a thin low velocity layer at the plate interface, probably within the predicted lock zone of the Cascadia megathrust, and it seems to be a very robust feature of this joint inversion. So with that, I'm going to just summarize kind of some of the data takeaways and results takeaways, but these are things that I've already mentioned in my talk, so you can kind of just look over them. But really, most importantly, what we're planning on doing in the future. So right now, most of the shallow structure is constrained primarily by only receiver functions. We're planning on incorporating shorter period ambient noise and compliance data to get more refined constraints on what, especially the sediment structure is beneath these stations. And then, of course, we're going to expand this across the entire array that I showed you. So we'll actually have a shear velocity model that covers the entire Juan de Fuca plate. And then, of course, interpretation of seismic velocities as physical parameters like temperature, composition, hydration. And for this, I'm really excited because there's so many other people working on this data set using various seismic techniques. There's people working on magnetotelluric, an ambient, offshore-onshore magnetotelluric data set in this region currently that spans the lock zone that overlaps with this. There's a lot of interesting active source seismology that's being done where people are looking at what the velocities of sediments that are beginning to go down with the plate look like. And so thinking about both my results in the context of all of these other really interesting geophysical results that are going to be coming out of both the Cascadia Initiative and other experiments is going to be really, really interesting. And I'm looking forward to doing that. So, thank you.
All right, thank you. Questions?
So you started with this issue of how broken up the Juan de Fuca plate is. So there, I mean, it's understandable given that that ridge is approaching the continent and it's trying to get out of the way. But you didn't follow that through. Is that the origin of all those sedimentary basins? These are structures in the Juan de Fuca plate that are behaving differently and making sedimentary basins?
So what the hypothesis for the sedimentary basins was basically that if you have a megathrust earthquake, so this is based on observations where sedimentary basins in other subduction zones seem to overlap with the regions of highest slip in megathrust earthquakes, and so they then extrapolate it to Cascadia. But the idea would be that where you have high slip in a megathrust earthquake, that leads to some subsidence of the overriding plate, and then those sedimentary basins fill because you've had subsidence, and so the sedimentary basin is an indicator for where there was highest slip. Is one interpretation of these features.
Because there are these issues with the structure of the plate itself.
Right.
The fracture zones there. There's this low velocity anomaly that appears in the arc just south of the Washington-Oregon border.
Yeah.
That God only knows what it is. But
yeah.
The interest is in extrapolating it to the structures of either downgoing plate or rips in the plate. Some misbehavior of the plate going down. So I'm just curious if you saw that offshore.
Yeah, I mean, I think, like I said, the actual inversion is ongoing. And so you can start to look at, these phase velocity maps are particularly useful for starting to kind of infer what some of the velocity structure might be. The danger with this, though, is, like I said, they're sensitive to kind of a wide range of depths. And so you really do need to, you don't want to interpret this strictly in terms of, oh, this is shallow depth, oh, this is deeper depth, because it's kind of actually smeared out. And so, as I said, with those sedimentary basins, these features could be features that extend with depth, but also if you have just very slow velocities at the surface, that feature can actually bleed through all of these different periods. And so that's why you really do need to actually do the depth inversion to see where these features are coming from. But I think, once we finish the inversion for the shear wave velocity structure with depth, we are going to have a pretty nicely detailed view of whether or not some of these features are superficial or if they extend with depth. So that's where we're going with that.
To follow up on that, it seems like a lot of the trick is going to be to get rid of that pressure component, right? So both to get the shorter period ambient noise stuff, you get crustal structure and basin structure.
Yeah.
But then also for the receiver functions, it was striking how many white dots there were for the deep water station.
Yeah, and so one thing I will say, for the full joint inversion between the receiver functions and the surface waves, we're primarily focused on using that technique on the shelf and then onshore. Probably offshore, we are not going to use that technique because, one, the receiver functions are very poor, and also they don't tell you much, because the main thing that you use for the receiver functions with the surface wave, it's nice because it gives you a detailed crustal structure, and it's also nice because you need some sort of a crustal correction to make sure you're interpreting your mantle velocities correctly. But offshore, we have already a pretty good idea of what the oceanic crust looks like from all the active source surveys that have been done in the region. There's stuff that has gone all the way from the Juan de Fuca Ridge to the trench in various places. And in general, those surveys tend to see a pretty consistent thickness to the oceanic crust for the Juan de Fuca plate. So we can probably actually safely just put in a crustal constraint, maybe supplemented by some constraints from compliance data. But the receiver functions themselves probably wouldn't give us that much more information about the oceanic crust in that region than what we don't already have.
So for the velocity structure of the oceanic crust, you're mostly waiting for the shorter period ambient noise?
I think we're not really waiting on anything. I think we were just more excited about the joint inversion, so that's what we worked on first. But yeah.